Hello everyone, my topic of presentation is reducing cache misses by compiler optimization. So, how can we improve the performance of cache? In short, how can we optimize the performance of cache? Parameter to measure performance of cache is AMAT, average memory access time, which is calculated by the formula hit rate into hit time plus miss rate into the miss penalty. In order to improve the performance of cache, we need to reduce the term AMAT, which can be done by the three ways: by reducing the hit time, second by reducing the miss rate, third is by reducing the miss penalty. In this presentation, I am going to concentrate more on the how can we reduce the miss rate. There are four popular techniques to do that. First, by increasing the cache size. Second, by increasing the associativity of the cache. Third, by increasing the block size in the cache. The fourth one is compiler optimization technique. In today's presentation, I am going to elaborate more on the compiler optimization techniques. So, what are the compiler optimization? Compiler optimization means the way in which code can be modified in your program to have fewer misses. This can be done by compiler also or by the user, coder or the programmer who is going to work on that memory. McFarlane back in 1989 reported 50% reduction in cache misses in 2 KB cache size and a 75% reduction in cache misses on 8 KB direct map cache. From this we can say that compiler optimization techniques are a very good solution to reduce the cache misses. Basic underlying working principle of this technique is we just need to reorder the instruction so we can have the less conflict misses. In this techniques, we work only on the software level, nothing we can change on the hardware level. So, how can we do that? There are four popular techniques for that. First one is merging of arrays. In this, we improve the special locality by single array of compound element versus two separate arrays. Second is loop interchange. In this, we change the nesting of loop while accessing the data. In this technology also, we improve the special locality. Third is loop fusion technique. In loop fusion, we combine the two independent loops that have same looping and the same variable overlap. Here we are using the same variable overlap, so we are improving the temporal locality. The fourth one is blocking. Improve the temporal locality by accessing block of repeatedly versus processing the whole column or the rows. So, the first technology I am going to discuss is merging of arrays. Merging of arrays is best applied if the elements of different arrays are located far apart from each other in a memory but usually accessed together. So here there are two elements. One is val and a key. They are stored separately like this in a program. By declaring like this, the val array will get stored completely like, and after that key array will get stored completely like this. If the sizes of this array are bigger than the cache size, we are going to definitely get the cache miss. After merging these two arrays, we are just changing how these two elements are getting stored in the memory. By merging these two arrays, first one val element is get stored, after that one key element is get stored, and after that one val, and after that one key element gets stored, and so on. Here, as in the program, val and the key we are accessing simultaneously. By changing the layout, in short by merging these two arrays, what we are improving the special locality. Here also we reduce the conflicts between the val and the key. In this way, merging of arrays will help to reduce the miss rate. The second technique I am going to discuss is the loop interchange. Consider these two are the loops which we use in the program. In the first type of looping, I variable it gets less nested inside the j variable, while in the second looping, the j variable gets nested inside the I variable. In both the type of looping, we are calculating the same variable with the same number of instructions. So what we are changing is just the looping. So what do you think? Which one is better? I or J or J or I? It depends upon how the data is getting stored in your memory. As we know, the computer memory is the 1D array. So there must be some mapping from 2D array to the 1D array. How the mapping is done? There are two two mapping methods. First one is row major and the second one is the column major. In the row major mapping, one row will get stored completely, after that second row will get stored completely, and so on. While in column major, first whole column will get stored completely, after the second column will get stored completely, and so on. In the C programming, the mapping is done by row major technique. So when we change the loop interchange in the C programming from this to this, what we are getting is sequential access instead of striding to the memory after every 100 words. If we do this looping in the C program, what we get is we have to just hop from one element to the other element, striding to the 100 elements in between. While changing this looping to this looping, we get the continuous data in the memory. What we are improving here is the spatial locality, and we are reducing the capacity misses also. By using the loop interchange technique, we are improving the cache performance but without affecting the number of instructions. In both the looping, number of instructions, number of variables are the same. Third method is loop fusion. Loop fusion method is helpful when separate section of code that access the same array with the same loops performing different computation on the common data. Consider here are two loops. In the first loop, we are calculating the value of a variable using b and c. In the second loop, we are calculating the value of d variable using a and c. After doing the loop fusion of these two loops, we are calculating both the variable in the same looping. Consider if we get a cache miss on c, there is also possibility of getting a cache miss on this c variable. So in short, we are getting the two cache misses by using the first looping. While after the fusion, if we get a cache miss on this c, we get a data from the main memory and we can access the same data in the next step. So what we are getting is 2 misses per axis of c versus 1 miss per axis. So we are improving the temporal locality and reducing the capacity misses. The fourth technique I am going to discuss is the blocking. Blocking is useful when we are going to access a multi-dimensional array. For example, matrix multiplication. The capacity misses occur if the all data cannot fix into the cache. Solution provided by blocking is we just divide a matrix into the smaller submatrix that can fit into the cache. Size of blocks is chosen depends upon the size of cache. And blocking can be useful for the certain types of algorithm. So here is the example of the blocking. While doing a normal matrix multiplication, we just try to the whole row and the whole column. If the size of this row and a column is bigger than the cache size, we are going to get definitely a cache miss. Instead of that, what we do is we just divide the matrix in a smaller subblock and we do the computation. And at the end, we merge this all the computation. So what we are improving here is capacity misses will get the less. This can be done by this methodology also. The capacity misses are reducing here from 2n cube plus n square to the n cube divided by b plus 2n2. So blocking is also helpful to reduce the capacity misses. In this also we are using the same variable again and again while doing the matrix multiplication. So we are improving the temporal locality also. So these are the effects and performance improvement we get by compiler optimization technique in various operating system or the kernel. Consider in the vPenta we are getting around 1.7 performance improvement by just using the merge array. So from this we can say that compiler optimization technique is a very good solution to reduce the cache misses, and we are not adding any hardware cost also. These are the reference I use while doing the presentation, while making the presentation. Thank you.